จอลงมา Can you hear me? Hello? Okay, let's start the makeup class for today. So this is the second time we use the YouTube for our makeup class. Sorry that I forgot to click the send button for the announcement. And maybe most of you didn't receive my announcement, but you can watch the video after class. So today we are going to finish the chapter 11, the chapter for the paired t-test. Right? After that, we are going to have a review of all of the z-test and the t-test, and as a summary. Right. So Monday, we introduce what is a paired t-test, right? So the paired t-test is used for the data obtained from a repeated measure design. So in the repeated measure design, or we call it the within subject design, right? We have the same group of people participant in the study, and they are used in all of the treatment conditions. So for paired t-test, there are 2 conditions in total. So for the repeated measure test study, we have one group of participants and 2 scores for each participant. Right. So for this kind of data, we are focused on the difference score. Means the difference between the score before treatment and after treatment for each subject, right? So we compute the difference score for each subject, and based on all the different scores, we call it D, right? We can compute the mean of different score, we call it MD, and use the MD, and we can do the t-test, right? To test whether or not the mu D is significantly different from 0 for a two-tailed test, and whether or not the mu D is greater or smaller than 0 for a one-tailed test. So for the repeated measure test, t-test, right, we use this formula to compute the t-value. So to compute the t-value, we need to know the mu D, right? So we just said we compute the D for each subject and then calculate its mean as the MD. So the mu D here is always 0 based on the non-hypothesis. Right, for the SMD means the standard error of the mean difference value. So we have to use this formula. First, we compute the variance of the D, right? And then we compute the standard error of the MD, which is SMD. And we follow this step, and then we can compute the t value. So on Monday we stop here. We introduce an example for a repeated measure design, right? In this study, right, all of the participants experience both conditions. One condition is the swearing, and another condition just to repeat the neutral word. And we measured their levels of pain. And here is the data. You can see we have 2 scores for each subject, and then we compute the mean, the difference, right? The difference scored D for each subject. And then here the first step is to state the hypothesis, right? So this is the hypothesis for 2-tailed and 1-tailed test respectively. And then we located the critical region based on the degrees of freedom and the alpha value and the type of test, 1-tailed or 2-tailed, right? And then we compute the t value, use this formula, just follow the previous steps, compute the MD to how to compute the SMD, right? So we computed SSD first, and then we compute the SD, and then we compute the SMD. So after we know MD and SMD, and then we can know the T value, which is -3. So compared to the boundary of the critical region, we know this value is located in the critical region. Therefore, the decision is, so if it's a 2-tailed question, and then we said the levels, pen level, they are different between these 2 treatment conditions, right? So if it's a 1-tailed test, and then we can make the decision that, make the conclusion that swearing can significantly reduce the levels of pen compared to repeating the neutral words. So last time we stop here, and if you don't have any question for this example, so let's continue. Now I'm going to introduce the assumptions of the related sample t-test, right? So there are 2 assumptions of this test. The first one is the observations within each treatment condition must be independent, right? So see here, so we know here is for the within each treatment conditions. And inside each condition, the score are obtained from different individuals, right? So we never obtained in each treatment conditions, we just have 1 score, right, for each subject. And in another treatment condition, we have another score for this subject. So within each condition, the scores are independent between subjects. And another assumption is the population distribution of the D scores, right? The D value, the different scores must be normal. So they are the 2 assumptions. And then let's do some learning check for this part. Here we have the first question, right? So in this question, here we have 2 treatments with 1 sample of n equals to 9 participants. So 2 conditions, 1 sample means 1 group. So it is a within subject design or repeated measure design. So we have to use the paired t-test, right? And then here we know the MD and we know the SSD. So the question is about what's the T value. So we just use the formulas. We know we compute the S first. SD is the variance, no, the standard deviation, right? So we compute the variance, which is the square of the SD, which is the variance of the difference score, which equals to SSD divided by the DF. So DF, which equals to SSD divided by n minus 1. Right. So for a paired t-test, the degree of freedom is just n minus 1. Here is 288 divided by 9 minus 1, and which is 36. And then we can we know the SMD means the standard error of the MD equals to the square root of SD square divided by the n. So which is the square root of 36 divided by 9, which is square root of 4, which equals to 2. So we know the SMD equals to 2, and T equals to MD minus mu D. Divided by the SMD, which equals to MD, we know, which is 5. 5 minus mu D is always 0, divided by 2, and then we know it's equals to 2.5. So we have the answer 2.5, which is B. Right. Okay, so we finished the question 1, and then let's start question 2. Right. So for repeated measures study, compare 2 treatments with n equals to 15 scores in each treatment condition. The data produced t equals to 1.78. If the mean difference is in the direction that predicted by the researcher, then which of the following is the correct decision for hypothesis test with alpha equals to 0.05? So here we are asking about whether or not this t value is located in the critical region, right? So to determine the critical region, we need to know first, right, the distribution of the t, so which is determined by the df. df here n equals to n minus 1, which equals to 15 minus 1, which is 14. And the second factor is the alpha value, right? Alpha, where's the alpha? Alpha here. So we know the alpha here equals to 0.05. And here we are asking about whether is one-tailed or two-tailed. And then we need to use the T table, right? To search what's the T value as the boundary of the critical region. So here we go to the line which is 14. df equals to 14 and 0.05 for the one-tailed. Here we know one-tailed because this here we know the t is a positive number. So for the one-tailed test, right? Because see here the data, if the mean difference is in the direction that predicted by the researcher, means they are on the same side, means the right-hand side, and then we can know the critical region is t greater than 0.05, which is 1.76, and a two-tailed t. Two-tailed t here, this number, right? Either smaller than negative 1.45 or t greater than positive 2.145. Okay, we know the boundary of the critical region, right? And then we see here the t equals to 1.78, and then we can see it for the one-tailed t-test, it is in the critical region, but for the two-tailed t-test, it's not in the critical region. So our answer is we can reject the num for the one-tailed test, but not for the two-tailed, which is A as the correct answer. Okay, so now here we know how to do a t-test, right, for repeated measure design. And then let's introduce how to compute the effect size and confidence interval for repeated measure t. So we also have three measurements of the effect size. First one is Cohen's d. Right, for the Cohen's d, we usually use the sample mean difference divided by the sample mean deviation. So here is the mean of the d score. Here is the standard deviation of the d scores. And for the R square, which measures the percentage of variance accounted for the treatment effect, right? So the formula is exactly the same as other t-tests. For example, the one sample t-test and the independent measure t-test. So the formula are always the same. You just need to compute the t and the df. So you see here, because the standard deviation is independent to the sample size. So the Cohen's d will be not influenced by the sample size. And here, so the sample size influences df, right? But df is just as a part of right here. So the R square, the sample size has little influence for the R square. And this is the confidence interval. Here is for the estimated mu d, right? Means the population of the different score. So which equals to the MD minus plus T times SMD. So here MD is the center, right, of the mu d, of the confidence interval. And this part is the width of the confidence interval. here is the example, right? So we know something, and then let's compute the effect size. So first, we compute the Cohen's d. Cohen's d, which equals to the MD divided by the SD, right? So to compute and then, so we need to compute the SD first. SD equals to the SSD divided by the degrees of freedom. We have the formula here. I just copy and paste. And the SSD here equals to 960 divided by n minus 1. N equals to 16 minus 1. Okay. Which equals to the 64, and SD equals to square root of this value. MD here we know here is 6, and SD is the square root. Square root of 64 is 8. .75, so means it's a median effect. To compute the R square, we need to know first the T and know the DF, right? The DF we know is equal to -1 equals to 15. And for the T, we need to compute T. T equals to, right, have the formula here. So the MD, which is 5, oh no, 6, mu D is 0, divided by the SMD, we need to compute. So SMD square is 64 divided by the N, which is 16. Here equals to the square root of 4, which is 2. So we know the SMD here is 2, right? And so the T value equals to 3. And we can compute the R square. Okay, so you're asking about whether I'm going to give you the SS value in the exam, right? I will give you the raw score in the exam, and then you need to compute the SS value by yourself. So based on the chapter 5, you will know the SS, how to compute the SS, right? So we know the SS equals to the sigma B. sigma d square minus sigma, the square of sigma d divided by n. So this is the formula for the SSD. And in the exam, you need to use this formula. Okay, let's go back to this question. So we have, now we are going to compute the R square. We know that t equals to, right, 3, the t square divided by the t square plus df, which equals to the 3 divided by 3 plus 15. The 3 square. Equals to 9 divided by 9 plus 15 equals to 9 divided by 24, which is 0.375, means 37.5% of the variance in the scores, in the D scores, right, can be explained. It can be explained by the treatment effect. So, and then we are going to compute the 95 confidence interval for the mu D. So here for the 95% confidence level with BF equals to 14. The boundary, right? The boundary T equals to, so now we have to use the T table again. 95% means a two-tailed, right, distribution with 5% left in two tails, right? So here 15, we have 15, and then a two tails 5%, which is this number, x equals to 2.131. So we know this number, the t, and then we know this t, and then we can use this formula, the 95 confidence interval, 95 CI, we use CI in short, CI of mu D equals to MD T S and D. So MD we know, which is 6 plus minus T we know is 3. No, T is not, sorry, this T 2.131 times SMD, which is 2. And then we can compute the width, which is 2.131 times 2 equals to 6 minus plus 4.264. And 6 plus, okay, what we can do here, which equals to 2.2 0.64, right? Which is 6 minus this number. And then the higher, the upper boundary, which is 10.66 plus this number, 262.64. And then we have the 95% confidence interval of the mu d. So we are done for this question. After we know how to compute the t value and the effect size, now we need to learn how to report the result in AP, use a sentence in the APA style. For example, we have this result, right? So that's what we computed. So we know the critical region, we know all of the statistic value, and we know the effect size. So let's write a sentence. This is for the example of whether or not the swearing, right, can reduce the perceived level of pain. So here, to write up these sentences, so you need to write in this way. First, changing from something, right? This is the treatment A, treatment 1, and to a swearing word, which is the second treatment, right? This is treatment condition 1 and treatment condition 2. Right here is the direction, significantly reduce the perceived level of pain. Right here is not an inferential stats. Here is a sentence for the descriptive stats. We are going to describe whether or not the MD is above or below 0. So if it's above 0, we said it's significantly enhance or increase something, right? If it's below 0, it's negative number. We said we're going to say it's reduced something or decreased something. And okay, so here, because of the descriptive stats, we cannot have significantly this word here, sorry. So reduce the receptive pain by an average of M, which is the MD value here, as 2 points, because we said it's reduced by 2 points, so we know it's a negative value. And then we report SD, right, which is the standard deviation of the MD, which equals to the square root of the SD square, right? So here the SD equals to 2, means the standard deviation of the D scores. And here is our inferential stats, is a sentence for the T test. So the treatment effect was significant, different from 0. Why? Because we see here the T value is located in the critical region, right? So it's significantly different because it's a two-tailed test. So we can just make a conclusion that it's significantly different from 0. We cannot say whether or not it's significantly higher or lower than 0. And then we report the T value, T parentheses, and degrees of freedom, and then equals to blah, 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 T value here, negative 3.00. And here, the P is smaller than 0.05. So for a two-tailed test, right? So the T value here is the probability we can obtain a T value greater than or smaller than this negative T. So because it's located in the critical region, and the probability of value located in critical region is 5%. Because it's in the critical region, and the proportion of the t, right, on the left-hand side below this t value is lower than 5%. So here we report it as p smaller than 0.05. And then after the p, t and p, we reported the Cohen's d here. And R, after Cohen's d, we reported R square here. And at the end of the sentence, we reported 95% of the confidence interval. Actually, it should be the next percent of insert. Should be the 95% of mu d of so we have to explicitly state the 95% interval of what? And then here is a sentence for the one-test test. If my question is whether or not, right, and swearing a word can significantly reduce the perceived level of pain. So you see here, from here to here, the descriptive stats part is exactly the same. And the difference is just here. So here we state it's a significantly different from 0. But here, for one-tailed test, we can state its direction significantly lower than 0. So you see here, just this word, right, is different between those sentences. Right. So here, I think lots of students have questions about what does the p smaller than 0.05 mean. So let me write the explanation here. P is for a two-tailed t-test, t with t smaller than 0. T is the probability of obtaining a t value smaller than the t statistics means. If the T is located in the critical region, the prob which is at a given of a given alpha level this probability should be smaller than alpha. So T smaller than alpha. So if we can, so it's the same thing, right? So if the P greater than 0, and then obtaining a value greater so they are the same, just on different tails of the distribution. But for a one-tailed t-test with t greater than 0, if the m is in the same direction as the prediction, if we predicted a positive effect and the data show also increase in scores after treatment. Right? T, the probability of obtaining T greater than T stats. Also the same thing. Let me see. The sentence. Smaller, so here. Means if it's located in the critical region. And then we write it as P smaller than alpha for all of these cases. all the above cases, if T is not located in the critical region, we'll report the result as P greater than alpha. Here EG P smaller than 0.05 if alpha equals to 0.05. So that's how we write this part, whether or not P is greater or smaller than our alpha level here. So then we are going to introduce the influence of the variance and the sample size in the repeated measured t-test, right? So we know a larger sample size produced a greater value of the t, means further from zero and increased likelihood of rejecting H0. It's exactly the same as what we said in the independent measure t-test, right? And also the same for the one sample t-test. Means a larger sample is always better, right? More sensitive for a t-test, any t-test, right? And larger variance produce a smaller value for the t statistics closer to zero and reduce likelihood to reject the H0. So this sentence is also exactly the same for all of the t-tests. And here, because in the repeated measure t-test, right? So we use the d scores, means different scores, as our measurements. So here you can say this is a smaller variance of the d scores, right? So you see here most of the scores are smaller than zero. The d scores are smaller than zero, means consistently we can have a negative treatment effect. But here, if we have a greater variance, right, in the d scores, this part, right, means some of them are very far from, are below zero, some of them are greater than zero, and their distance to zero are very, very large compared to the right hand side, this figure. So here, although their mean, they are the same, which is -2, the variance is bigger here, and means the treatment effect is not that consistent across subject in this sample, right? So here we know it doesn't have a stable treatment effect. I mean, some of them the treatment effect is sometimes the treatment effect is positive, right? But sometimes is negative. So here the variability can be considered as a measures of the consistency of the treatment effect. Means the smaller variability, a higher consistency of the treatment effect. For example, if you are going to test whether or not a medicine has an effect, right? And we hope the treatment effect will be very consistent, right? And then we can treat the disease. That the patients, they can recover, right, after they take the medicine, right? And then now, and that means we are expecting for smaller variability of the treatment effect. For example, this case. So let's do some practice. Here we know how to so we learned how to compute the effect size, and then we introduce how does the other factors influence the effect size and the hypothesis testing for a paired t-test, right? So in the first question, we are going to compute the Cohen's d. Just use the same formula. Cohen's d equals to md divided by the sd, right? And sd equals to here. Just replace the number of what we have in this example. No, in this question. Minus 1 equals to 39 equals to 6. So here we know the Cohen's d equals to 4 divided by 6 equals to 0.67. So the correct answer is D. Next sentence. No, next question. Here we are going to compute the 80% confidence interval for the population mean difference. Here, so to compute the confidence interval, this formula, right, we need to know the boundary T first. So in all of these options, the boundary T, they are the same. So that means we don't need to use the T table again. Right, and then here, what's the difference? Here, the center, they're different. Next one, the difference between options, right? And then the SM, they are different. So means we are going to compute the MD and the SMD. MD we know, which is 12 points. So these two, they are wrong. These two options, they are wrong. And then let's compute what's the SMD. So the SMD equals to, we know the SSD right here. Based on the SSD, we can compute the SD square, which equals to and then after that, we can compute the SMD, use this formula. 9 divided by n, which is also 9. So we know the SMD equals to 1. Okay, so we know the MD, right? MD, we know the T, we know the SMD, MD, T, SMD, the SMD, T here. So the correct choice is D. Okay, here we have the report, and then we are going to interpret this report. Miss something. We know here the p is smaller than 0.05, right? If p is smaller than the alpha value, means which means the treatment effect is. T smaller than 0.05, which means the treatment effect, it is significant, right? So here we know it is significant. And here is the DF value. DF, for the tail of the t-test, repeated measure t-test, the DF equals to n minus 1. So if we know the DF equals to 18, and then we know the n equals to 18 plus 1, which is 19, right? So D is the correct choice. We have 19 participants, and the mean difference is significant. Right. So which of the following would have little or no influence on effect size as measured by the Cohen's d or by R square? We just said the sample size, right, has no influence on the Cohen's d and has little influence on the R square. So the correct answer is sample size. Here we said the variability as a measurement of the consistency for the treatment effect. So here we know there it is a significant difference, a significant treatment effect. Means the variability should be very small. So it should be a small standard deviation. And if a consistent difference and the a larger difference of variance scores and a smaller standard deviation. So, right. If the standard error is small and we know the standard deviation is also small, so the variance is also small. The variability, both variability and the standard deviation and standard error are the measurements of variability. So the correct choice is A. And let me take 5 minutes break. I'll be back after 5 minutes. Okay, I'm back. So the last part, let's compare the repeated measured and independent measured t-test. So here, the number of subjects we need for the two different design, they are different, right? So here, the repeated measured study, we have one group of subject, right? Participant in both of the treatment conditions. So we need fewer subjects than an independent measured design, just as half of the sample size. And the repeated measured design is especially well suited for study learning development or other changes that take place over time. For example, you have the same subject. You can test this one when before learning and then test their scores after learning, right? Or test before a therapy and then test again after therapy. And also, because we just use one group of participants in the repeated measure design, so the individual difference will not influence, right, the difference between treatment conditions, because we just have one, they are the same individuals. So here is an example, right? So for the contribution of the individual difference to the sensitivity of a t-test, means the likelihood to reject the H0. So you see here, the values, they are exactly the same, right? But here is a repeated, independent measure t-test. Here is a repeated measure t-test. And then we can compute the t-value for these two examples. For example, for the independent measures design, we can compute the SP pooled variance, right? SP square equals to SS1 plus SS2 divided by the DF1 plus DF2, which is 114 plus 86 divided by 26 minus 1, and then 21 minus 1, which equals to 200 divided by 45, right? Which is 4.4. And then the S M1 minus M2 equals to did I use the correct formula? Let me check. Yeah. Yes, it's correct. The square root. Where's my square root? Of SP squared divided by M1. Plus S two squared divided by the N2, which equals to 4.4 divided by equals to square root of it's wrong. Sorry. What's that? So the t value equals to M1 minus M2 divided by the SM1 minus M2, which is really? Did I do the computation correctly? Come on. Ah, here I know what's wrong. Why? 3 minus 3. Sorry about that. That's why I feel so weird. We have 3 subjects. Why I write here 26. So the square, so it should be 50. 50. Divided by 3 times 2 and take the square root. So which is negative 0.86. I use the same data for the repeated measures design, right? And then we can compute the t value again. So we know that, so use the same formula, copy and paste. Use this formula The SSD we know is 8, divided by n minus 1 is 2, which is 4, right? And the SMD, which equals to 4 divided by 3, which is 1.15, and the T equals to which is here mu D we know is -5 divided by 1.15. So you see here, the T value is much further from 0 compared to the T value in the independent measures design. So for degree of freedom, we say degree of freedom as 4, right? 4 here, and the 2 test with 0.05. So the critical region is T smaller than negative 2.266, or T greater than positive 2.776. And then we can know the decision here not in the critical region. So we know P is greater than 0.05, right? Means not significant. Here, for degree of freedom as 2, for repeated measure design, use the same data set. So we know here the critical region is T greater than 4.303. So our decision here is, smaller than the negative, or greater than. It is in the critical region. In the critical region, it means P is smaller than 0.05. It means significant. So based on this example, we see here, even though the data there, the raw data, they are exactly the same, right? We have exactly the same 6 values between these two examples. But if we use independent measure design, and the treatment effect is not significant. If we use a repeated measure, means within subject design, and then the treatment effect, it is significant. So means the repeated measure design is more sensitive to detect a treatment effect. But this is primary disadvantage. We introduced a lot of advantage, right, of repeated measure design. But what's the disadvantage for this kind of design? So The primary disadvantage of the repeated measure design is the structure of the design allowed for factor rather than treatment factor to cause a participant score change from one treatment to another. For example, right, we have the order effect. We always have one treatment condition before another treatment condition. For example, the before therapy condition is always right before the treatment, the therapy, before and after therapy condition. So in the fourth order effect, maybe because before therapy is their first time to do this task, they are not familiar with the task, and so their performance worse. But after treatment, it's the second time they perform this task, and then they learn how to do the task. That's why they perform better. So this is a potential confounding factor, right? The order effect. So we have an important way, right, to control this order effect. We call it as counterbalance. For example, we ask half of the participants to finish treatment B before treatment 1, and ask another half of the subject finish treatment 1 before treatment B. So, and then we counterbalance the order effect. Means half of participants finish treatment 1 before treatment 2. So this is a definition of the counterbalancing. The counterbalance is very important for experimental psychology. Okay, let's do some learning chat. So here we're asking about what's the advantage, right, of a repeated measure design compared to the independent measure design. It's reduced the contribution of the error variability due to is the individual difference. Because the MD, they are the same, just the difference between the mean, right? So if we have the same data set, for example, based on this example, the MD, the different scores, they are exactly the same, which is -5. And the effect of treatment is the effect size, right? It's also just due to the mean. So the effect of treatment is not. And degrees of freedom, you see here. So for between subject design, the degrees of freedom is bigger, and the boundary, right, you see here, is closer to 0. So it doesn't reduce the contribution of the error variability. So but here in the repeated measure design, we use the same group of subjects. So we reduce the variability of the individual difference. The second question, we are asking about the advantage of a repeated measure independent measure design means it's a disadvantage for the repeated measure design. So we just have one disadvantage, is the time-related factor or order effect. So the correct answer is B. Right, so ask about when we prefer a repeated measure design. So see here, so the repeated measure design is more sensitive, right, to detect a treatment effect. So when the treatment effect is very small, and then we just have fewer subjects. And also we have the individual difference are big. We prefer the repeated measure design. So the answer should be D, because we just need fewer subjects in the repeated measure design, and then the individual difference has less influence on the significant level, right, compared to independent measure design. So we finished this chapter. And then I'm going to give you a summary of all of the t-tests and also the z-test, means to compare means, right? The approach we use to statistic approach we use to compare means. So the first slide here is the data structure of these four kind of tests. In the z-score test, right, what we know, that here means what we know, and then here have nothing. The empty cells means what's unknown. So for z-score test, we know the mu before treatment and the sigma population standard deviation before treatment, and we assume the sigma doesn't change after treatment, but we don't know the population mean after treatment. What we know is the sample mean after treatment and the sample standard deviation after treatment. So for z-score, when to use z-score means when we just have one group, one sample of subject, and then we have one observation for each subject. Also, we know the population mean and population standard deviation before treatment, and then we need to use the z-score. Here, for one sample t-test, right, you can see here other part, they are exactly the same as the z-score, but just as this cell, they are different. So for one sample t-test, we don't know the population standard deviation. So means when we just have one sample, one observation for each individuals in this sample, and we know the population mean before treatment, but we don't know the population standard deviation before treatment, then we have to use the one sample t-test. For independent measure t-test, you see here, we don't know all of these population parameters, but we know the sample statistics, the mean and standard deviation for two groups. Here we have, when we have two samples with different individuals in each sample, and we have one observation from each subject. We want to compare the mean between the population mean, right, between these two groups. Then we need to use the independent measure t-test. So for paired t-test, other parts, they are the same. But we just have one group of subject. We have two observations from each subject. So in this case, we use the paired t-test. Right. Based on the data structure, we can design which task, we can make the decision that which test to use. As we said, the purpose of all of these tests are to compare means to compare the population mean between before and after treatment. And the statistic value, it can be a z value or can be a t value. This is the general structure of the formula of the statistical value. So the general structure is the sample data minus the hypothesis, right? And then this terms divided by the error. So the statistic value can be considered as a ratio between the treatment effect and the error term. Here we list each component for each design, the components for each design. For example, for a z-score test, statistic value means here on the left-hand side of the equal sign is z. And the sample data here is the population mean after treatment. The hypothesized the population parameter, which is this term, is the population mean before treatment. The standard error means the error term here. We use this formula to compute. And this is a sample variance, right? We need this term to compute the sample, the effect size. I forgot to copy off the formula here. Right. So after this class, I will copy all the list of the formula here and post it to the Blackboard. And the degrees of freedom of a z-score test is n-1. You can see here this is the statistic value for one sample t-test is a t, right? And also for other t-tests. On the left-hand side of the equal sign is t. And the sample data here is the m. The hypothesis population parameter is mu. The standard error is the standard error of the sample mean. The sample variance we estimated as the S&S, right? The degree of freedom is n-1. So these are all of the components for an independent measure t-test. So we use the pooled variance as the variance of the difference between M1 and M2. For paired t-test we just introduced, we focus on the difference score means x2 minus x1, the difference between the scores before and after treatment for each subject. So here is the formula. You can take a note for all of these tables, and maybe it's easier just to search these tables when you're going to do something in the exam. So these slides are assumptions for each test, right? For z-score, we have 4 assumptions. The one is the random sampling, means we randomly sampled individuals from the population. And the second one is the independent observations, means the observations is independent between one another. And the third assumption is the sigma is unchanged by the treatment. You can see here, so we don't have this assumption for all of these t-tests. And the fourth one is the normal sampling distribution, means the scores, the distribution of scores should be normal. So you see here the independent observation, we have this assumption for all of the test, right? And also the normal distribution, we have this assumption for all of the statistics value we're interested in for all of the tests. And then just we have one additional assumption for independent measure t-test, which is the 2 populations from which samples are selected from have equal variance, which also called the homogeneity of the variance. This one is the unique assumption for an independent measure t-test. After finish the assumptions, and then this slide we compare the effect size, right? How to compute the effect size. So for the z-score, we just have one measurement for the effect size, which is the Cohen's d. Use this formula, and the Cohen's d always as the difference, right? Before and after treatment, divided by the standard deviation. So in the z-score, the standard deviation is the population standard deviation. And this is the formula for the one sample t-test. We replace the m, no, here they are the same, but replace the population standard deviation by the sample standard deviation because we don't know the population standard deviation. And then for independent measure t-test, we use the square root of the pooled variance as the estimated standard deviation. In the paired t-test, we use the standard deviation of the d-scores as the standard deviation. And then you can see here for the r-squared, the formula, they are all of the formula, they are the same for all of the t-tests, but we don't have the r-squared, right, for the z-test. The confidence interval always as the center plus minus the width. So the center for one sample t-test is the sample mean. But for the independent and paired t-test is the difference, right, between sample means. And the t is determined by the level, the percentage of confidence. SM is the standard error of the mean of. So this is the standard. This is the error term, right? Always at the center plus minus, right? The boundary times the error term. Okay, here we are talking about the influence, right, of these factors our statistics. Okay. So the influence of the difference between two population mean, right? Here the plus sign means the population, the positive relationship means if, for example, the difference increase, and then we have a greater T or Z value, and we also increase our likelihood to reject H0. We also have a bigger coherence D, a bigger R square. But here, the difference between the population mean will not influence the width of the confidence interval. Oh, here I missed. CI here means confidence. It's confidence interval. Equals to. Other factors, they don't influence the center, right? And then if we have bigger difference between the population means we also have greater power. So anybody remember what's the power? Okay, we're asking about if significance is the same thing as rejecting the hypothesis. Yes, so significance it is the same thing as to reject the H0, means the non-hypothesis. So we know the sample mean difference, right? The influence of sample mean of this. And then there's the influence of the variance. So you can see here, bigger variance is not good for hypothesis testing, right? Because it's reduced likelihood to reject H0, means it's reduced the likelihood of obtaining a significant result. And also, it's reduced the coherence D, means the samples, the effect size, right? Both coherence D and R squares, they are effect size. But it does not influence the center of the confidence interval. It makes the width of the confidence interval larger. Means we are less confident about our estimated, right? Estimated statistics, the estimated parameters, population parameters. We are less confident, and also reduce the power of the statistics. The sample size is good for hypothesis testing. A greater sample size will increase the T or Z value, and then therefore increase the likelihood to reject H0 means increased probability to identify a significant effect. But it does not influence the effect size, the coherence D, and just has little influence on the R square. It does not influence the center of the confidence interval, but a bigger sample will produce a narrower confidence interval. Means we are more confident about our estimated population parameter. And also it increased the power. So the power is related to the type 2 arrow, right? Type 2 arrow is the false negative, means when there it is an effect, but we fail to detect that treatment effect. So here's a summary. Maybe it's helpful for you to answer some question in the design. And in the problem set part, means the open book part, I will give you just one question for each category of design. One question. So one for the z-score, one for the one sample t, one for the independent t, one for the paired t. For each question, you need to follow the 4-step approach. Means first step, you have to state the hypothesis. Tell me what is the H1 and what is the H0 and what is the H1. And I will give you the alpha level. And then the second step, you need to determine the critical regions and write on your exam. So what is the critical region? And then you compute the statistical value. So either the z value or a t value. The last step, you make a decision whether or not it is significant. So here I list the non-hypothesis and the alternative hypothesis and the critical regions for all of the designs, and for two-tailed and one-tailed tests respectively. So you see here, the hypotheses, they are exactly the same, right? For the z-score and the one sample t-test. And this is slightly different, right, between an independent measured and paired t-test. And see here, so if I ask you whether the treatment effect produce an increase in the score or produce it is a decrease. And then you need to do a one-tailed. So here I can also merge cell. Maybe it's produce significant difference. So if I ask you whether the treatment produce a significant difference in scores, then you use a two-tailed test, right? If I ask you whether the treatment produce a significant increase or a significant decrease in scores, and then you need to do a one-tailed test. You just follow this way to state the non-hypothesis for each categories of test. And here I also list all of the degrees of freedom and the critical region. So for a z-score, right, because the z-score are always in the normal distribution, So the critical region or regions are only determined by the alpha level. And whether or not it's a two-tailed or one-tailed test. Just two factors. One is alpha level. Another one is this one-tailed or two-tailed test. It's for the z-scores. But for a one-sample test, right here, you can see here the critical region are determined by three factors. The degrees of freedom, because it determines the shape of T distribution. The second factor is the alpha level. The third factor is a two-tailed or one-tailed test. So in the exam, maybe I will ask you the critical region is determined by how many factors, right, for a certain test. And then you need to know. So if you want to take note, you can just take screenshot, or you can watch the videos again, or just download the slides from the Blackboard and print out this page. Here is how to make a decision, right? It's the same as what I just write. Here is the same. So if the statistic value is located, what time is it now? Okay. Located in the critical region, right? If for two-tailed test, and if the Z or T score is greater than a positive boundary or smaller than the negative boundary, or in the one-tailed test, if right here, and then the probability of obtaining a statistical value is not lower than alpha. So this means that the probability of obtaining a statistical value is lower than alpha, means it's very unlikely to obtaining this kind of T or Z value. So we write it as P smaller than alpha. For example, P is smaller than 0.05. Therefore, our decision is to reject the H0. And we can make this conclusion. So that's how to make a decision. If not, right? If not, means P is greater than alpha, then we can make the decision not to reject H0, and there's no significant effect or no significant something, right? No significant increase or no significant difference. If not, thank you. P greater than here to reject 0. No. So that's how to make a decision. So that's it for today's class, and thank you for your watching. I'm going to give a review for the exam 2 on next Monday. We are going to have the exam on next Wednesday. So see you next week.